Okay, welcome back. Hopefully, you just watched the first video on the introduction of Solver and optimization. And if you haven't, I would encourage you to go back and make sure you've watched that first so that you've got context for this one. Assuming you've done that, all right, let's get to it. Now, what you want to do is have that little scavenger hunt list nearby. I'm talking about objective function, variables, coefficients, constraints. And if you do, that's great. We're going to tick down the list. If not, I'll try to bring those back in our little example today. So the first things first, when we get a problem and we get it, if we get it into in a narrative format, I mean in a paragraph with words and things like that, we probably want to take the time to put it into a diagram before we do anything else. And that's so that we can visualize the problem. So in supply chain land, we always like to refer as the left side of our paper as upstream, and farther down to the right of the paper as downstream. So that puts things into perspective. And in our network or our problem today, we're going to start out very, very simple, hopefully so simple that it'll be very easy for you. And the thing about modeling is that you want to begin simple. You really don't want to dive into a very complicated model right off of the bat. And it's very hard to validate it and troubleshoot it, and especially if you're new to modeling, you really can't tell what's going on. So we're going to start out very, very small with a problem in which we have a manufacturer. We have two manufacturers. We're just going to call our first manufacturer M1, and our second one is going to be M2. And then we're going to say that we have two retailers, and we're going to call them R1 and R2. Okay? And so as far as our network goes, we could ship product from manufacturer 1 to retailer 1, or we could ship product from manufacturer 1 to retailer 2. Let's say that we have that in the narrative and we're just putting it into a drawing. And by the same token, we could ship product from manufacturer 2 to retailer 1, and from manufacturer 2 to retailer 2. And so we're going to call this the amount of units that goes from manufacturer 1 to retailer 1. Along this route, we're going to call that channel 1. That'll refer to the number of units that move along that route. And by the same token, we'll call the number of units that move from manufacturer 1 to retailer 2, we'll call that channel 2. And then we'll call this channel 3 and this channel 4. And so these refer to the amount of units that go on the respective route. And these are, I'll pause and see if you can say it before I do. These are our decision variables. And these are the things that we're going to tell Solver, hey, based on this other information, we want you to come up with the values for these decision variables. Okay. Next thing we're going to talk about within this problem, we have some costs involved. So it's given to us in the narrative. We have some costs. That so we pull out of the narrative that on channel 1 it costs $1.20 per unit that moves along that channel. And on channel 2 it costs 1.4. On channel 3 it is 1.1, and on channel 4 it is 1.5. Okay, and like I said in the last video, that means if we send 500 units on channel 1, the cost would be 500 times 1.2. So these are our coefficients. And eventually, when we write out, if we were to write out our objective function, we would write it, minimize the following equation. 1.2 C1, see how that's that coefficient for that variable, plus 1.4 C2 plus 1.1 C3 plus 1.5 C4. And every time, for example, where this is written 1.5 C4, that implies that we're taking the value that solver is going to find for C4 and multiplying it by that 1.5. And then we're adding it to the value of C3, multiplying that by 1.1, and so on and so forth. Okay, so there's our objective function, minimize cost, and cost is defined by those respective values for the decision variables times their respective coefficients or costs. Okay, so that takes care of variables, that takes care of coefficients. We have our diagram for our network. Now, we want to identify arguably the most important part, which is the constraints. So let me get set up for that. So I've gotten rid of my coefficients. Hopefully I've got them parked somewhere else, or you do too. And I realize these are my variables. I also removed my objective function just so I've got some space here on the screen that I can write, because I'm going to use it up. So first we need some givens on the capacities for the manufacturers. And in this problem today, I think we're going to use 60,000 as the amount of units that manufacturer can produce, and 56,000 as the amount of units that manufacturer 2 can produce. So the first set of constraints, which is what we're going to do now, is to identify our supply constraints or capacity constraints. And I think the easiest way to do this is to work and stay consistent in working upstream to downstream. And as I like to say, we're going to have all our alligators facing upstream is what it's going to end up doing. You may be going, what does that mean? Well, we'll explain what that means as we go along. So our first supply constraints is that capacity, we'll start with M1, has to be equal to or greater than the amount that we ship out of manufacturer 1. So we can't produce less than what we ship. We have to either produce just as much as we ship or produce more. And that's what this means right here. And of course, the amount that we ship out of manufacturer 1 is C1 plus C2. So that's our first supply constraint. Now we'll do our second one, which is really just dealing with manufacturer 2 in this model. So we're going to take that 56,000. And again, our capacity has to be equal to or more than what we ship out. Can't ship out more than what we produce. And so we ship out of manufacturer 2 this amount and this amount. So we have C3 plus C4. Now here's what I was talking about earlier. Our alligators are facing upstream. See that alligator right there? And that was an idea coined by a warrior I worked with named Darby Hetrick. And Darby, if you're out there somewhere, I hope you are doing well. Anyway, and a crew of folks, warriors that she ran around with, who I won't go into all of them. But I hope you all are doing well as well. So now we just keep working downstream. So we kind of reverse this. The amount that comes into, let me back up one second and say what our demand is. And for those of you who were able to catch class the other day, these numbers here for demand and capacities very well may be different, but that part doesn't really matter. It's the process. So we'll say that demand here is 42,000 and demand here is 34,000 units. So we're just going to work our way downstream, but slow is fast, as we like to say in the logistics and operations world, meaning that we got to be careful not to mess this up. Now, if we stick with the alligators facing upstream, if we position things right, everything will go good. So what's coming into, let's start with retailer 1. What's coming into retailer 1? Retailer 1 receives from channel 1 and channel 2. So if we say C1 plus C3, well, that has to be at least equal to, if not greater than, what our demand is. So in this model, if we don't tell Solver to at least meet demand, if not exceed it, then Solver will do some other things. So we're telling Solver that the amount that retailer 1 receives must exceed, be greater than 42,000, which is its demand. And the amount it receives comes from those two channels. Super. So by the same token, let's address retailer number 2. And that is retailer number 2 gets its receipts from channel 2 and channel 4. And by the same line of logic, those receipts must at least equal retailer 2's demand of 34,000, if not exceed it. So we have our 2 supply or capacity constraints, and we have our 2 demand constraints. And now within this model, the other one we need is what I talked about up front, which is what's called non-negativity. So we need C1 to be greater than or equal to 0. We shouldn't have any negative units going along this route. And the same holds true for all the rest of our decision variables. So we need to tell Solver that we need these variables to be at least greater than or equal to 0. And that's our non-negativity constraint. Okay, and this is arguably the toughest part of the pre-work before we go into Solver, and that completes the pre-work that we need to do before we go into Solver. So just to quickly review, first thing we did was if we had a narrative, we pulled out of that narrative what we needed to set up our problem visually so we can understand what our network looks like. We can put it in terms of upstream to downstream. We can see capacities and we can see demands as well as the channels that connect the network. Then we can identify the constraints, our supply constraints, and our demand constraints. And then we make sure we apply non-negativity where it needs to be. And as a little technique, I like to work upstream to downstream. You see how all the alligators are facing upstream. We could face them all downstream if we wanted to. We just need to flip everything around. For me, we worked upstream and then we continued upstream to downstream. We're always working upstream to downstream. Okay, so that includes our pre-solver work. And in the future, for the warriors that I work with, I will require you to show that you have identified all this pre-work in addition to the nuts and bolts inside of Solver. And that way, we're going to build a solid foundation on modeling using the optimization technique. So that concludes this video. I will see you very soon for video number 3, where we're going to jump inside of Excel. We're going to take our network diagram with us. We're going to continue to build in Excel, and we're eventually going to bring Solver out of the cave. See you soon.